60 tons per lift, 6 containers high, thousands of cycles without structural failure. These port vehicles handle forces that would buckle ordinary steel, yet every critical joint is held below 70% of the metal's yield strength. They move at 25 kilometers per hour around the clock, and they don't break. But only 4% of the world's terminals are fully automated. Understanding why starts inside the steel itself. A single straddle carrier hoists 60 tons in one lift, enough weight to match nearly 40 family cars stacked together. In the span of a minute, it can move a loaded shipping container the length of a soccer field and then position it with pinpoint accuracy. These machines are built to stack containers 6 high, forming steel walls that tower over the terminal. Yet the ground beneath each wheel must support a load equal to a city bus. Operating at 25 kilometers per hour, a carrier can shuttle between ship, truck, and storage yard, repeating the cycle thousands of times before major maintenance is required. Every movement is a test of both strength and precision. The gantry frame must absorb the shock of a fully loaded container settling into place without twisting or cracking. To prevent fatigue, no critical joint is ever allowed to approach the metal's yield point. Engineers design for a safety margin that keeps stress below 70%, even during sudden stops or emergency maneuvers. This relentless repetition, lift, drive, stack, repeat, demands a structure that can withstand more than 1 million cycles over its service life. Versatility is built into the core of the design. Straddle carriers aren't limited to one task. They transition seamlessly from serving the towering ship-to-shore cranes to loading trucks and reorganizing stacks in the yard. Unlike fixed cranes or rail-mounted machines, they can move in any direction, adapt to shifting yard layouts, and respond to surges in cargo flow. The result is a vehicle that makes the scale of global trade tangible, turning raw tonnage into a daily routine and raw steel into a backbone that never buckles under pressure. Maya Patel leans into the dashboard, eyes tracing a digital map of stress fields rendered in deep blue and red. The finite element analysis model shows every weld, every bolt, and every joint under simulated loads, 60 tons at a time, 1 million cycles over the carrier's life. The numbers tell a story. Even at maximum lift, the highest stress reach only 70% of the steel's yield limit. This deliberate margin isn't just theoretical. It's enforced with every load, every emergency stop, and every hard turn across the yard. The carrier's gantry frame never risks creeping into the danger zone where cracks or fatigue could begin. Structural integrity is only one half of the equation. The other is endurance, measured in kilowatt hours and peak output. Each electric straddle carrier is powered by a 175 kilowatt-hour lithium-ion battery pack, delivering up to 300 kilowatts at full tilt. That's enough to hoist a loaded container, accelerate to yard speed, and keep moving for up to 10 hours on a single charge. The battery's design balances energy density with weight, ensuring the carrier stays nimble without sacrificing runtime. The digital controls monitor every parameter in real time: voltage, temperature, current draw, and cell balance. If a spike or anomaly appears, the system reacts instantly, limiting output, triggering cooling, or alerting maintenance before a fault can cascade. This closed feedback loop, paired with predictive analytics, has pushed mean time between failures for electric drivetrains to over 22,000 hours, far beyond older diesel models. For Maya and her team, the dashboard isn't just a display. It's a living record of the machine's health, confirming that every cycle, every shift, is within safe, engineered limits. The result is a platform that can absorb the relentless pace of port logistics day after day without structural compromise or unexpected downtime. On June 25, 1993, a new era began at the edge of Rotterdam's Maasvlakte. That morning, the world's first fully automated container terminal officially opened its gates. Queen Beatrix presided over the ceremony, but the real stars of the day were the machines. A fleet of 58 automated guided vehicles, each weighing about 14 tons and designed to move containers with no human driver. These AGVs formed the backbone of the Delta Sealand Terminal's operations, quietly linking ship-to-shore cranes with the sprawling yard. Each vehicle could carry either two 20-foot containers or a single 40-foot unit, handling loads up to 28 tons per trip. Power came from onboard lithium-ion battery packs, recharged automatically through induction systems embedded in the charging lanes. This setup allowed a full shift, 12 hours of continuous work, before a recharge was required. The AGVs received their marching orders by radio, connected to a central terminal operating system. This software assigned routes, managed load assignments, and tracked the location and health of every vehicle in real time. Communication flowed both ways. The system could reroute an AGV to avoid congestion or pause operations if a fault code appeared. The control architecture was layered for resilience. Device-level firmware managed motors and safety sensors, middleware aggregated telemetry, and the central TOS handled scheduling and inventory. In case of a radio blackout, each AGV could fall back on its own navigation maps, returning safely to a charging point. During the first year, the fleet maintained over 96% uptime, a figure that set a new benchmark for automated logistics. The launch of the Delta Sealand Terminal was not just a technical achievement. It provided the first proof that a fully automated yard could handle the relentless pace of global trade without continuous human intervention. This milestone would become a reference point for every automated port project that followed, transforming the logic of container handling from manual muscle to digital precision. A straddle carrier's reliability depends not only on steel and battery, but on the invisible intelligence guiding every move. Modern automated guided vehicles, or AGVs, now rely on a navigation stack that fuses multiple sensor inputs for centimeter-level accuracy. At the core is RTK GPS, real-time kinematic positioning, which delivers absolute yard coordinates with less than 10 centimeters of error. This allows an AGV to chart a direct path through a maze of stacked containers, even as the yard layout shifts throughout the day. LiDAR sensors, spinning at the corners of each chassis, scan the environment in 3 dimensions, detecting obstacles as small as a misplaced traffic cone or as large as a 40-foot container. Each AGV processes millions of data points per second, building a live map of the yard and adjusting its route on the fly. Radar systems take over when fog, rain, or dust obscures the LiDAR's view, ensuring that the vehicle never loses track of metallic objects or moving equipment in low visibility conditions. All of this data is managed by an edge computer running a motion control stack, which can stop or reroute the AGV in milliseconds if a hazard appears. At the Port of Long Beach, a fleet of 102 AGVs operates entirely under this sensor-driven autonomy. The vehicles communicate over a dedicated 5G network, which delivers sub-10 millisecond latency, fast enough for real-time fleet coordination, collision avoidance, and dynamic traffic management. Maya Patel, overseeing the latest retrofit, monitors the system's digital twin, every AGV's position, battery status, and task queue update in real time, allowing for predictive maintenance and seamless handoff between machines. This networked intelligence is what enables the yard to run 24 hours a day, with each vehicle executing thousands of moves per shift without a driver in sight. The result is a system where autonomy is not just a technological aspiration, but a daily operational reality, setting the stage for the next breakthrough: automated energy replenishment. At the automated battery swap station, the choreography is precise and relentless. As Maya Patel confirms the carrier's arrival on the control panel, a robotic gantry glides into position overhead. Safety interlocks engage, sealing the work zone and verifying that voltage and temperature are within safe bounds. The gantry's 6-axis arm unbolts the depleted battery module, lifts it from the carrier's underframe, and slides it onto a charging cradle. In one continuous motion, a fully charged pack is lowered into place, guided by alignment sensors that ensure high current contacts engage cleanly. The entire swap, including disconnect, removal, insertion, and safety checks, completes in under 5 minutes. This rapid cycle keeps each carrier available for nearly 95% of a 24-hour shift, minimizing downtime and eliminating the need for long charging breaks. The process is repeatable, tightly monitored, and engineered to keep the flow of containers moving without interruption. Fewer than 4% of the world's container terminals operate with full automation. For Maya Patel and her colleagues, this number is both a benchmark and a question mark. Even after decades of technical progress, autonomous vehicles, real-time sensor fusion, and predictive maintenance, the vast majority of ports still rely on manual or semi-automated operations. The reasons are complex: high upfront costs, integration challenges, and the need to tailor systems to local conditions. Yet every new automated terminal proves that round-the-clock, driverless cargo movement is possible at scale. As the technology matures, the question is not whether full automation works, but how quickly the rest of the industry will follow. The next chapter in port logistics remains unwritten. Global trade now depends on machines engineered for relentless precision, systems that withstand millions of cycles with less than 5% downtime. As ports race toward full automation, the real test lies not in moving containers, but in maintaining flawless reliability at scale. The future of logistics demands nothing less.